Okay, finally, there's going to be a medium today. Alright, check if a string contains all binary codes of size k. Given a string s and an integer k, return true if every binary code of length k is a substring of s. Every binary code, what does that mean? Is a substring of s. Every binary code of length 2. So the binary codes of length 2 are 0, 0, 0, 1, 1, 0, and 1, 1. They can all be found as substrings of indices 0, 1, 3, and 2 respectively. Every binary code of length 2. Okay, so binary code just means every possible binary string that is of length 2. So all the numbers that are basically 0 to 2 to the second minus 1, so 0 to 3. Here it's not because you don't have 2 zeros. Here it is because you have a 0 and a 1. Okay. I think I understand. K can be pretty large. K is 20, then you could possibly have 2 to the 20th binary codes. That's a lot of binary codes, right? But then the length of the string is pretty large too. I mean, I guess you would just do a sliding window, the window being K. So you have, you're looking at a sliding substring K length and then keeping track of it using a set maybe. Using a set and no, using a set might be too. I mean, yeah, using a set is fine. I guess it's not possible if 2 to the power of k is shorter than the length of the string, or is bigger than the length of the string, right? Because I don't. If you had something that's 2 and there's only 3 characters, then there's no way that there's going to be 4 different versions of the substrings. So I think the trivial case is going to be not possible if 2 to the k is bigger than length of string, because each character in the string is basically contributing one possible thing, one possible binary code. If 2 to the power of k is greater than length of s, return false. Yeah, I guess I'll do a sliding window. Do values as a set. Sliding window. Sliding window for sliding window for tracking to track all values generated from k substring, k length substring. guess if you're using sliding window where you're going from left to right, you need to incorporate what the next zero means and then remove the previous zero, and remove the leading value. How do you track that is the thing. Add a zero, or you add the next value, which means it doubles the previous stuff. And then it needs to remove the highest. It needs to remove the highest. So I think maybe if I use a queue, where the queue stores where the ones are. Queue stores where the ones are. Yeah, I guess that comes to mind, a queue. To track where ones are in window. So like if this is 2, then you have a window that's 0, 0. There's no ones here. And then 0, 1, and you keep track that there's a 1 at this index. I guess since you're just tracking ones, maybe you just keep track of the index. So 1 at index 2, and then a 1 at index 3, and then here you would remove the 1 at index 2. So you take away that value from the from the values in the window. So let's say I have my index. I guess I need to have the current value. Current is equal to 0. Let's say answer equals 0. No, there's no need for answer. Current equals 0. Current being the current value of everything in my window. For index in range n. Actually, I think this needs to be initialized for index in range k minus 1. How big is k? K is up to 20. Okay, fine. For index in range k minus 1, current equals current times 2 plus plus 1 if s at this index is equal to a 1, else just 0. I think I need to have an else. Yeah. And then for every index, so this is the initialization, this is the actual sliding part. So for everything in range k, from k to n, so I need to also have my queue, double-ended queue. Indices of ones in window. So I think this should be, well, I guess should be current equals current times 2. If s at index equals 1, string 1, then current plus equals 1, and the deck appends this index. Yeah, I think that's right. And then here, same process. So I'm gonna add. So normally for sliding window, it's going to be add new, add right value to window, check everything, basically your invariant, and then kind of then remove left value from window. So add right value to window would mean that I do current equals current times equals current equals current times 2 if s at index equals 1. Same thing as above. Current plus equals 1 deck appends this index, and then check it. So the invariant doesn't need to be checked, I don't think. So whatever values, add this current value, and then remove the left from window. So if this was a 2, k is 2, and it's like 1, 1 currently, and you're moving to 1, 0, that means that whatever index this one is at, it's now outside the window, so you need to remove that. So remove so I think I need to check the indices. If deck at 0, so this can be the front window or front index, is smaller than index minus k plus 1. So if this is 2, I'm at index 0, 1. I incorporate the 0, and then I incorporate the 0 index 1, and then I need to remove this 0 and index 0. So 1 minus 2, 1 minus 2 is negative 1 plus 1. I think it's less than or equal to. Actually, I guess this just means, yeah, I think it's less than or equal to. 1 minus 2. I guess this could also just mean index minus k plus 2, but whatever. Then what I need to do is I need to remove this value. So current, well, I need to also remove the thing. Deck dot pop left. And then current needs to reduce by 2 to the power of k minus 1. K is 2, then it needs to remove 2. 2 to the second minus 1. 2 to the power of k minus 1. I guess maybe I should just keep this as a remove, the remove value, because that's always going to be there. It's gonna be the same. I think that's it. Return if the length of this set of values equals 2 to the k. If it is, then it's true. Okay. Deck out of range. Oh, right. Sometimes it could be empty. Interesting. Okay. Let's see what's going on here. Never got 0. Really? Current times 2 should be 0. K is 2. 0. Oh, it should be k minus 1, I see. Not inclusive, not inclusive. Alright, I think maybe this works. We'll see, we'll see. Works, but isn't very fast. Okay, I guess, I mean, a deck is kind of... guess, yeah, a deck is overkill, right? Because the index is a certain value, and you're always using index minus k plus 1, so you're always going to look at... Yeah, you're always going to look at a certain value before it, a certain number of indices before it. Yeah, okay, so... I guess I don't need to keep track of this. I just need to look at string at this index, maybe. String at this index is equal to 1. Okay. Sometimes you just need to code it to see that it works a certain way. Alright. What else could I do here? Keep track of my current values. Iterate over the initialization. I mean, I guess I could do something where this thing's just spliced, taking a slice of the string, converting it to an integer, rather than... Oh, that's not true. Slice the string, have to convert it from binary to integer. Wonder. looks fine. Current times equals 2. Increment. If it's a 1, and then add that value to my current value. I guess I could do a short circuit right here. I can check if the length of values equals 2 to the power k. Then break early. As I expect a lot of times it probably is going to, or a fair amount of time it should exit. I guess I can just do total is equal to 2 to the power k here. At that point I can just return false otherwise. Really depends on the distribution of test cases if this is going to be proven. Okay, I guess maybe. I guess just a check is not going to be very slow. Asset index minus remove left value. This is probably fine. Yeah, okay, I think yeah, I need to keep track of the set. And here you can't really create you can't track it using an array because actually if the array is too big then it's probably going to return false immediately here. So I guess you could keep track of it with an array, but there's probably just going to be overhead as well there. Keeping track of how many uniques you've seen. Okay, so summary here. So this is a sliding window to track the value currently the integer value, or yeah, the integer value of current k length binary code substring. Use a set to keep track of all unique values and compare it to the total possible values for k length, which is going to be 2 to the power of k. To see if it satisfies the condition. So for sliding window, iterate over right index, kind of last index of right side window. incorporate that bit into the value. So for instance, if you have 1, 0, and you want to incorporate a 1, 0, 1, then that's the value 1, 0 is 2, 1, 0, 1 is 5. In order to go from 2 to 5, you go 2 times 2 plus 1, where the 2 is doubled, and then you add an extra 1 bit. Incorporate that bit into the value, i.e. 2 times current value plus the bit. Then add current value to set. You can do an optional check for end condition here, or you can do it technically after the loop. And then lastly, you remove left side value from window. So you have to remove this 1, assuming k is 3. So which is always going to be, will always be 2 to the power of 2 to the power of k minus 1. And that's pretty much it. You get to initialize the window to the correct size as well. Because here, if it's something before k index, then you don't have a left side to remove because it's not window size yet. Alright, anyways, time complexity, this can be O of n, where n is the length of the binary string, since you need to iterate over every index in the string to add to window. Constant work inside loop, the sliding window loop. Base complexity can be O, I think it's O1. Oh no, sorry, O of n. No, O of, technically the way I did it, I think it's O of 2 to the power of k. Since the set that is used to track the unique values will cap at the number that it requires, which is technically less than n, because I have a blocker for when it would be bigger than n. But yeah, when it immediately finds that hits its goal, then it stops. Here, note 2 to the power of k. Actually, I guess this should be min, the minimum between this and n, because I do, in theory, 2 to the power of k could be, which is always less than n due to the check for trivial case.